Hey guys, in this particular video I'm going to walk you through a relatively simple dynamics problem which really needs the use of the formula we derived in a previous video for circular motion. So this is the particular problem. Say we've got this rotating rod right here, and this rod is rotating at a constant angular velocity in the counterclockwise direction, right? Around this fixed pivot point O, right? So this is our fixed pivot point. And then when this rod actually makes its full revolution and goes to theta is equal to 0, right, then we decide to place this red block on here. And we notice that when the block reaches an angle 60 made from the horizontal, right, then we notice that the block begins to slide. And my question to you is, what is the coefficient of static friction? How can we use the information we've got to calculate the coefficient of static friction? Well, first let's start off with some intuition here. Because we placed the block here at an angle theta is equal to 0, the block is roughly around here, that means the block will swoop out a circular path, right? It will swoop out a circular path with a radius r. Well, that's not the only thing we know. We also know that the direction of static friction will be trying to prevent movement of the block. So it will be facing up the slope of the rod to try and prevent the block from moving down the slope. Alright, now that we've got that aside, let's see if we can actually try and solve this particular problem. And of course, our first step, as we probably should be really aware of now, is to draw a free body diagram. So here's our free body diagram of our block, and I've drawn it extra large just to really see all the forces in full detail. So this is our block right here on a slant. What are going to be the forces acting on this block? And let me scroll down a bit. Well, you're going to have a force due to gravity, right? That's going to be this force. This is your force due to gravity, right? And that's going to be mg, right? What else? Well, you're also going to have a normal force, and this free body diagram shows all the forces acting on the particular block at any time mid-flight. So this could be any time between theta is equal to 0 to 60. I really want to generalize this as much as possible. So this is our normal force right here, right? And as a result, we've also got a friction force, which is going to be in this direction, right? And the friction force will change depending on the elevation of the rod, but for now we'll just leave it as FF, denoting our friction force. And there's a really important thing to know from this, and that is when theta is equal to 60, which is when the block begins to slide, that means that your maximum friction force will be overcome. So in other words, a threshold limit, really, is theta is equal to 60, theta is equal to 60 degrees when your friction force is going to be equal to mu Sn, right? Remember that mu Sn is a maximum friction force, right? Anything more, if there's another force which overcomes this, then it will just slide. So we know that when theta is equal to 60 degrees, that's when we're dealing with our maximum friction force. Okay. And I probably should mention that while the block is moving, the block begins to slip relative to the rod. I mean, that just prevents someone from saying, well, the block is always moving. But no, I mean, like, relative to the rod, the block starts to move at 60 degrees. All right, well, how do we solve this question? There's no easy way to. It doesn't seem like there's any easy way to solve this, but there is. We just need to recall this particular formula, and recall I derived it in a previous video, and that is the acceleration of any particle traveling in a circular orbit is going to be equal to your radius of your circular path times by your angular acceleration in your tangential direction. Right? That's what each of these terms mean. Right? ET is just your unit. Is just a unit vector in your tangential direction. So this just denotes that r alpha is in the tangential direction, and this is going to be plus v squared on r, where v is actually a speed. It's very misleading. V squared on r, right? And that's going to be in your normal direction. And remember, in the video where I derived this particular formula, your normal direction is directed towards your circle. So let me draw that on here, just in case you can't visualize that too easily. This will be your tangential direction right here, right? Tangent to your path, and this will be your normal direction towards the midpoint of your circle, right? So this will be, actually let me draw that. This will be n, and this will be t, denoting normal and tangential, right? Okay, I hope that makes sense. Okay, well, now that we've got that sorted, is there any other formula which can help us? Yeah, Newton's law. We know that the sum of forces acting on an object is going to be equal to the mass of that object times by the acceleration of that object. Notice that these are vectors here, right? So we can like simplify them into their separate directions, and we could simplify them in x and y, but it'll be easier to simplify them in tangential and normal. So what I'm going to do is I'm going to separate this Newton's law into tangential and normal components. So in other words, we can say that the sum of forces in our tangential direction is going to be equal to the mass of our object times by the acceleration of our object in the tangential direction. And the sum of forces in our normal direction is going to be equal to the mass of our object times by the acceleration in our normal direction. And because we know the block is traveling in a circular path, that means that we know that our an term, and I should make this clear, this is a subscript n, our an term is going to be this, right? This is our acceleration in our normal direction. This is our scalar an, right? And this right here, this coefficient is going to be at. Our component of acceleration in our tangential direction and our component of acceleration in our normal direction has to be equal to this because it's traveling in a circular path, right? I proved that in a previous video, so I definitely recommend, if this makes no sense to you right now, that you hit up the previous video I made. Okay, well, let's see if we can simplify this a little bit more. What is the sum of forces in our tangential direction? Well, I mentioned before that our tangential direction is like this, and let me draw it right here. Our tangential direction is like that, and our normal direction is like that, right? I don't want to make you think that they're forces, so I'm going to delete them, but essentially that's what I'm trying to say, right? So how can we use this to try and figure out the sum of forces in the tangential direction? Well, to do this, we need to write the force due to gravity in its two components. Its component in the normal direction, which I'm drawing now, and its component in the tangential direction, which I'm drawing now. And because this line right here can be continued all the way onto the origin of our pivot point, that means that we know this angle right here is going to be theta, right? Meaning that we know that this angle here is going to be theta, meaning we know that this angle right here is going to be 90 minus theta, which means we know that this angle here is going to be theta, right? And of course this is a right angle triangle, and that's why. Okay, well, using trigonometry now, and I'm going to delete this because it clutters up the scene a little bit. And using trigonometry now, we can work out the component of our force due to gravity in our tangential direction. It's just going to be mg cosine theta. Likewise, our component of gravity in our normal direction is going to be mg sine theta. Okay, well, that's interesting enough. Let's see if we can simplify this a little bit more now that we've deconstructed our force due to gravity in both its normal and tangential components. Let me just draw a dotted line to really show that this is deconstructing our force vector. Okay, well, let's see if we can figure this out. What's one force in our tangential direction? It's the normal force, isn't it? Is there any other force? Well, yeah, it's the component of gravity in the tangential direction. So it's going to be n. It's a force in the tangential direction minus mg cos theta. Mg cos theta, right? Cos theta, because mg cos theta is in the negative tangential direction, and that's going to be mat on the left-hand side, right? Well, like I discussed before, the right-hand side can be simplified to m times, and what's at? It's just going to be r alpha. Alright, and the left-hand side stays where it is. It's just going to be n minus mg cosine theta, right? Okay, well, let's see if we can figure out this anymore. I've been told in the question that our angular velocity was constant, right? In particular, I think I mentioned, yeah, our angular velocity is 2 radians per second. That's how fast it's rotating, and it's rotating at a constant angular velocity. So omega is a constant, right? Specifically 2 radians per second, but for now, it's just a constant. Omega is a constant. And recall that d omega dt d omega dt is alpha. I proved this in a previous video, right? As such, what's the derivative of a constant with respect to time? Or, well, respect to anything, really. Well, it's 0, right? Imagine taking, like, ddt of 4, right? It's just 0, right? Consequently, alpha is equal to 0 because omega is a constant. I hope that makes sense, fellas. Consequently now, we can actually write alpha is equal to 0, which means that this right-hand side term is 0. Notice this would have been very different if our rod was rotating with an angular velocity that was a function of time. Alright, consequently now we can simplify this even further, writing that n minus mg cosine theta is going to be equal to 0, right? As such, we can say that n, our normal force, which is acting on the block from the rod, is going to be mg cosine theta, and that's as far as we can get with that particular formula, right? That's going to be huge, right? That's a really interesting formula we can use. Well, now that we've exhausted that to its dead end, let's see if we can explore the other formula right here. Let me just block that off. How do we explore this formula right here, the sum of forces in our normal direction? Well, very similar to the way we did it before, it's going to be, well, what are our sum of forces in our normal direction? Well, we got our friction force, which is up. What about anything else? Well, yeah, we got our component of gravity, which is down, right? So that's going to be mg sine theta, and order is important here, mg sine theta minus our friction force, right? And we've done examples of this earlier, so I definitely recommend, if this is like too outlandish for you, you look at my previous videos, right? And that'll be equal to m times an. And remember, an is just, as you can see here, the magnitude of our velocity vector squared divided by the radius of your circular path, right? Okay, well, let's see if we can figure this out anymore. And don't forget that this free body diagram was drawn for anywhere between 0 is less than theta is less than 60, right? This is anywhere mid-flight from when the block was put on to where the block starts sliding, right? Consequently now, we have to say that this is true for anything between 0 is less than theta is less than 60 degrees, right? But, and here's the kicker, right? Here's the kicker. When theta is equal to 60 degrees, which is when the block starts sliding, that means our friction force is going to be mu Sn. It's our maximum friction force preventing movement, right? And that's exactly where the block starts to slide. So if I can actually write this now, I can actually say mg sine theta minus mu Sn is going to be equal to mv squared on r when theta is equal to 60, right? When theta is equal to 60 degrees, right? Because that's when the block starts to move, which is when we're going to be invoking our maximum friction force. Okay, well, this may seem quite simple, and all you really need to do is literally just solve for mu s, and watch me do it, because it's pretty simple mathematics at this point. I'm sure we're pretty comfortable with algebra, so I'll do it in one step. That'll be mg sine theta minus m times your speed squared on r, right? That's the speed of your block moving in its tangential direction, and that will be, well, in order to work this out, oh, sorry, this is all going to be divided by n. I forgot to do that. Alright, consequently now, notice that we've got this n, pesky n, sitting in the denominator, right? Well, fortunately for us, we calculated what n was equal to in the previous set of equations we had. So consequently, we can make that substitution now and say that mu s is going to be mg sine theta, or remember, theta is 60 in our case, minus mv squared on r, all divided by mg cosine theta. And this next step will probably give you a small refresher of high school mathematics, but remember, if we divide both of these numerator terms by mg cosine theta, notice that the mg's cancel off for our first term, but what's sine theta divided by cosine theta? It's just tan theta, right? Tan theta. That's a small refresher of high school mathematics. And that's going to be minus the magnitude of our velocity of our block squared divided by, and the m's cancel off, so it's going to be rg cosine theta. Cosine theta. Fantastic. Alright, well, let's see if we can simplify this a little bit further. Recall in a previous video, I proved that the magnitude of our velocity of an object traveling in a circular orbit is going to be equal to the radius of our circular orbit times by our angular velocity, right? Consequently, now we can simplify this expression even more so and say that our mu s is going to be tan theta minus r omega squared, right? Because it's the magnitude of our velocity squared divided by rg cosine theta. Cosine theta, right? And notice the r's cancel off a little bit. Notice that the r's cancel off, so that will be tan theta minus r omega squared, only the omega squared, g cosine theta, where in our case theta is equal to 60, right? And this is our answer. This is a very generalized solution to our problem, and this is mu s. Mu s. Fantastic. So this is a very generalized solution. If we wanted to calculate the specific solution to our problem, all we need to do is plug in our values. So recall, theta was equal to 60. Theta was equal to 60. R was equal to, what was it? What was R equal to? R was equal to 300 millimeters, which is 0.3 meters. 0.3 meters, right? Because I only want everything in SI units. Omega was 2 radians per second, which is a standard unit of measurement. So that's going to be 2 radians per second. Radians per second. What else? Well, we know. Is that it? Well, notice that our mass isn't involved here, so that's quite interesting because it proves that this problem would be the same regardless of whether the block was 10 kilograms or 1,000 kilograms. Alright, well, let's plug in the values. That's just going to be tan 60 minus 0.3 times by 4, right, 2 squared, divided by 9.81 times by cosine 60. Cosine 60. And that will give you an answer of, in our particular case, our mu s, our coefficient of static friction, is going to be 1.487. And notice, it's a dimensionless unit of measurement. Alright guys, that's this problem sorted. I might do one more video which is going to be significantly harder, and it's probably going to be related to polar coordinates. Alright, thanks guys.